and welcome to video 8.3.1, our first lesson on periodic trends. So the first thing we have to do before we get started is familiarize ourselves with these definitions. So the first one is Coulomb's law, and Coulomb's law states that the force is directly related to charge and inversely related to distance. So K is some constant, Q1 and Q2 are our two charges, and d squared is our distance. So we can see that the stronger the charges, the more attracted they are to each other, but the farther apart, our force and our attraction drops off quite quickly. Our core electrons are any electrons in the inner shells. So the ones that are closer to the nucleus are the inner shells. They're involved in what we call shielding, and they are non-valence electrons, so they're not really involved in bonding. Valence electrons are in the highest shell, or in the shell farthest away from the nucleus. These are involved in bonding and also ion formation because they can be gained and lost. Nuclear charge is denoted with a capital Z. That's the number of protons in the nucleus. The effective nuclear charge is Z effective, the little EFF down there at the bottom. That describes the charge of the nucleus that's felt by the outer electrons. So those outer electrons don't feel the entire charge of the nucleus because some of those inner core electrons shield it, and that was that shielding effect we talked about. And so to get that, we would look at the total number of the charge of the protons in the nucleus minus the core electrons, and that's a Z effective of any electron toward the outside. Shielding is the blocking of nuclear charge by core electrons. Ionization energy is the energy required to remove an electron from an atom. So if we go from atom A to the ion plus an electron, so we've removed an electron, we had to put energy in to do that. Electron affinity is the energy that's released when an electron is added to an atom. So any atom plus an electron forming an anion here, that's when we had to take energy out. And electronegativity is kind of a balance of the two. It's a combination of ionization energy and electron affinity. And basically it just tells us how much an atom wants an electron from another one. So it's how greedy it is kind of for electrons. And that's kind of a tug of war between ionization energy and electron affinity. All right, let's go ahead and start taking a look at all these trends on the periodic table with those definitions in mind. So right now what I'd like you to do is please pause the video, and I would like to see if you can fill out this entire chart. Now, the thing you need to remember here is the core electrons are every electron minus the valence outer electrons, and Z effective you can calculate using your equation above. So go ahead and pause now and then come back and check your work. Okay, I'm going to write all the short form configurations. So for lithium, that is helium. And it's okay if you didn't write the short forms. You could have written the long form as well. So that's helium plus 2s1. Sodium is neon and 3s1. Potassium is argon, 4s1. And we're starting to see a trend emerge here, right? Rubidium is krypton, 5s1. And cesium, finally, is xenon, 6s1. Okay, so there's all our electron configurations. So how many protons do these have? Well, it's the same as the atomic number on the periodic table. So reading those off, I have 3, 11, 19, 37, and 55 for cesium. How many core electrons do these have? Well, for this whole one, for lithium, we have 2 core electrons, and our Z effective is going to be 1. So we have a total of 3 electrons here. In the 1s shell, we have 2 electrons, so those are the inner ones. And then the 2s shell, which is our valence shell right here. These are all going to be our valence shells, right, because they're on the outside. We're only going to have 1 electron. So for sodium, if we have 11 total, and we have 1 valence, we should have 10 core electrons. For potassium, if we have 1 valence, and we have 19 total, we should have 18 core electrons. Same for rubidium. We still have 1 valence, 37 minus 1, 36. We have 1 valence in cesium, 55 minus 1 is 54. Okay, and then we can see that the atomic radius here, as we go up from lithium, as we go down a family, from lithium to cesium, the atomic radius gets larger. That means these atoms are getting bigger. Their ionization energies are decreasing. So we're going from a higher ionization energy to a lower one. So in general, when going down a family, the atomic radius will increase. It increases. And the ionization energy decreases. The effective nuclear charge for all of these, well, if we look at it, is exactly the same. However, there are more core shells and outer electrons in higher shells. So there are more core electrons in the outer shells. Okay, so number 2, explain why the ionization energy of boron, which is 800.6 kilojoules per mole, is greater than that of aluminum, which is only 577 kilojoules per mole. Well, first let's find these on the periodic table. Well, here's boron, and here's aluminum. So we can see that the trend we're going to care about here is going down a periodic table. And so we know, because we're told, that the ionization energy of boron is higher than aluminum. So that means, if we look back at ionization energy, the energy required to remove an electron from the atom is greater. And the question is why? So I want you to please pause the video and think about why that might be. Keep in mind Coulomb's law when you're thinking, and then come back and check your work. Okay, welcome back. So if we look at boron, the outer electron in boron is in the 2p orbital. But if we look at that outer electron, or the valence electron in aluminum, that is going to be in the 3p orbital. So since electrons in lower shells, or inner shells, are more attracted to the nucleus, they're going to require more energy to remove. And therefore, boron's going to have a higher ionization energy. And that has everything to do with Coulomb's law. Because if we look at this distance over here, if they're not very far apart from one another, they are going to be if they are closer together, they're going to be harder to remove. If they're farther away, they're going to be easier to remove, because the force of attraction isn't as great if they're farther apart, which is the case in aluminum. Its electron is farther away from the nucleus than boron's is. Boron's is much closer. So boron's is pretty attracted to that nucleus, and it's going to be harder to remove. It's going to take more energy to do so. So let's go ahead and see if we can summarize that. The outer electron in boron is in the 2p orbital, while that of aluminum is in the 3p orbital. The electrons that are in lower shells, or really inner, but you say lower as in lower energy, are more attracted to the nucleus and require more energy to remove. Therefore, they have a higher energy, ionization energy. Okay, so that's trends down a family. Let's go ahead now and start taking a look at trends across a period. So for this example, we're going to be looking at trends going from sodium to argon. So if we look at that on our periodic table, we can see that's period 3 going from sodium all the way across to argon in the third period of the periodic table. So I would like you right now to please pause the video and fill this chart in exactly the same as you did for trends down a family. And don't forget to calculate your Z effective, and it won't all be the same on this one. And please do write the electron configuration in short form. Okay, go ahead. Okay, welcome back. Let's go ahead and get started. So I'm only going to write the valence. I'm going to leave out the noble gas notation on here just in the interest of space so we can see everything that's going on. I'm only writing the valence ones. So for valence, this is 3s, 1 for sodium. For magnesium, 3s2. For aluminum, 3s2, 3p1. For silicon, 3s2, 3p2. For phosphorus, 3s2, 3p3. For sulfur, 3s2, 3p4. For chlorine, 3s2, 3p5. And finally for argon, 3s2, 3p6. Okay. The number of protons, I just, again, read that from the periodic table. And these are nice and easy. These are in order. So 11, 12, 13, 14, 15, 16, 17, and 18. The number of core electrons in these is all going to be exactly the same. So it's going to be 1s2, 2s2, 2p6, right? So those are all going to be exactly the same. They have all of these same electrons for the first two periods of the periodic table. So it's going to be 10 electrons. That would be the neon that was in front of all of these. So if you were to write this totally correctly, you would have neon in front of all of these electron configurations. So to calculate Z effective, I just subtract protons from number of core electrons. 11 minus 10, 1. 12 minus 10, 2. Now you can see this trend continue all the way across the period. Okay, so for right now, I would like you to please pause this video and plot these points on the graph. So plot the ionization energies on the graph. Each line is 100 kilojoules per mole. So if I would label this, this is our ionization energy. And each line is 100 kilojoules per mole, so we can start at the bottom at 0. And let's say 100, 200, 300, 400, 500 here. 6, 7, 8, 9, 10, so 1,000 there. 1, 2, 3, 4, 5, 1,500 there. Okay, so please pause the video now. Go ahead and plot these points and then come back to check your work. Okay, welcome back. So I'm going to go ahead and quickly plot all of these points in a different color so it's easier to see. So for sodium, I'm looking at my ionization energy, 495. It's about 500, so I'm just going to go ahead and put my point there for sodium. Magnesium, 737. Okay, 6, 7, 37, right about there. For my aluminum here, a little bit lower, 577, so almost 600. Silicon, 786, so 5, 6, 7, 86-ish. For phosphorus, around 1,000. Let's see, sulfur, around 1,000. It's almost exactly the same. Chlorine over here, a little bit, so it's about halfway up. About 1250-ish. So 10, 11, 12. Sorry, I can't see the suns right there. About right there. And then our argon is about 1,500, a little bit over that. Okay, so if I go through, I just want to connect all my points here so I can kind of easily see where this trend is going. Okay, so here's my trend line. So I can see is that I'm going across a period. The atomic radius here, so if we look at our atomic radius, is going down. These elements are actually getting smaller as we move across this period. So the atomic radius decreases. And the ionization energy, so if we look at our ionization energy, in general, that's increasing. We have a couple little dips here, couple little inconsistencies, but if we look overall, it's going to increase. Now, of course, the million-dollar question, why does that happen? So what's happening to the atom structure among the elements going across a period, and how does that explain these trends? So right now, I'd like you to please pause this video, think about why that is, and then come back to check your work. Okay, so let's think about this. as we go across the period, the outer electrons of the elements are in the same shell. So right here, they're all in the same shell, right? And it's all in energy level 3. So the 3p3s. So since that's true, they have the same number of core electrons, in this case 10. They don't change. However, the number of protons changes. So as we move up, this nucleus is getting, or as we move across rather, the nucleus is getting more and more positive. It's getting more and more protons in here, right? So if we have more and more protons, we have a bigger positive charge. Therefore, your Z effective is going to increase. And since your Z effective is going to increase, the electrons are more attracted to the nucleus. If those electrons are more attracted to the nucleus, they're going to be harder to remove. Okay, so let's go ahead and summarize that in number 5. So going across the period, the outer electrons of the elements are in the same shell. So they have the same number of core electrons. However, the number of protons and therefore, I'm just going to use a little therefore symbol, the little 3 dots there means therefore, and therefore the Z effective increases. So that means the outer electrons are more attracted to the nucleus. Okay, let's go ahead and apply this knowledge now. So these questions for number 6 are something like you might see on a test. So provide an explanation for the following. The ionization energy of sodium is lower than that of magnesium. So let's go ahead and find these on the periodic table first. So here's sodium, here's magnesium. So we're going to look at trends across the period here. So why is the ionization energy of sodium lower than that of magnesium? Please pause, write down an answer, come back and check your work. Okay, so the answer for part A is that the outer electrons of both are in the same 3s orbital. So they're both in the same 3s orbital right here. So it holds 1 and 2 electrons. Now, magnesium, though, has 1 additional proton. So it's got 12 protons versus sodium's 11. Therefore, the valence electrons in magnesium are going to have a higher Z effective. They're going to feel more force and more attraction to the nucleus in magnesium rather than sodium. So that means that the valence electrons in sodium are less attracted to the nucleus. Therefore, they're going to be easier to remove because, again, that the proton charge is smaller. Okay, let's summarize. The outer electrons in both are in the same 3s orbital, but magnesium has 1 additional proton, not protein. Therefore, the valence electrons feel a higher Z effective in magnesium, which is 2, than in sodium, where the Z effective is only 1. So the valence electrons in sodium are less less attracted to the nucleus and are easier to remove. Okay, sorry about the sun shining on that page there. Okay, so part B. So the ionization energy of magnesium is higher than that of aluminum. So why then, if we said sodium is higher than magnesium, why is magnesium's higher than aluminum? So please pause the video, think about that, and then come back to check your work. Okay, so let's think about this one. Here the difference is we're going from a 3s to a 3p, right, for our valence electron. So the outer electron of magnesium is in the 3s, but the outer electron of aluminum is in the 3p. So the electrons in the higher orbitals, like the 3p here, take less energy to remove. Because 3p is higher energy than 3s, the ionization energy of aluminum is going to be lower. So the energy of 3p is greater than that of 3s, so the ionization energy is going to be lower. So let's summarize. The outer electron of magnesium is in the 3s orbital. While the outer electron of aluminum is in the 3p orbital. The electrons in the higher energy orbitals, like 3p, they take less energy to remove. Because they already have more residual energy in them because they are in a higher energy shell. So you have to put in less to get to that threshold. So they take less energy to remove. And since 3p is higher in energy than 3s, the ionization energy of aluminum will be lower. Okay, so last one here, part C. See if I can get rid of those lines. Oh, that's worse. Okay, so part C. The ionization energy of phosphorus is higher than that of sulfur. So let's go ahead and find phosphorus and sulfur right here, right next to each other. Why is the ionization energy of phosphorus higher than sulfur? Okay, go ahead and try that and then come back to check your work. Okay, this one's pretty interesting. This one might have been hard to think about. For this, I'd like to just write down first the electron configuration. So phosphorus has the configuration, well, its outer configuration with the valence electrons of 3s2, 3p3. That means in the p subshell, remember, if it has, so the p has like the 3 lines, if you remember, for the up and down arrows when we were filling. So this is half full. This p subshell is completely half full. Because we have 3 unpaired electrons. Therefore, there is low repulsion between those electrons. Because they're all in different subshells. And this is going to be a lower energy state. Okay, now let's compare that with sulfur. So if we write sulfur's electron configuration, 3s2, 3p4. So here, one of the 3p orbitals has 2 electrons in it. So one 3p orbital has 2 electrons. So it's got a pair of electrons in there. And that means overall we're going to have higher repulsion. Because remember, they're negatively charged and they're close to each other, so they're going to be repelling. So higher repulsion. And because there's higher repulsion there than if it was unpaired, that's going to require less energy to remove. So this is going to require less energy to remove than if it was an unpaired electron. So it's already repelling itself here. So you have to put less energy in because those electrons, they kind of want to get apart from each other already. So there's already higher energy in there. So therefore, you have to add less energy to the system in order to remove an electron from the sulfur, less than you would for phosphorus. And that's why the ionization energy of phosphorus is higher, because you need to put in more energy because it's relatively stable than here, where you already have one of those electrons wanting to leave anyway due to repulsion. Okay, so that is it for this lesson. I'll see you soon for the next one.